file security, and novel house-based Bitstream encryptions. Please.
Hello, Professor. Thank you. Can you all see my screen?
Yes. Very
Oh,
nice.
yes,
We
perfect.
have 15 to 20 minutes. Okay, 15 minutes.
It's
So
okay.
10
Yes,
minutes, we have minutes to have. Yeah, thank you.
thank you. Hello, everyone. Today, my name is Nikolaos Haralampidis, and today I'm going to present to you our paper exploring the future of file security. And in this paper, we introduce a novel chaos-based Bytestream encryption. First, we're going to start with some introduction, basically to introduce the problem and then a solution. And from that, 2, 3, and 4, 5 are we will present our main work and our main results, and then we'll finish this presentation with some conclusions for and future research. So, uh, what we're doing, basically, this mean we want to uh, make an encryption method, and of course, this encryption method should be also reversible through chaotic systems. And why we're using chaotic systems? Because they are deterministic, vulnerable to change, and they are also have small computational cost. And because of that, chaos-based cryptography has a ubiquitous applicability to random bit generators, watermarking, hashing, secure communications, and in particular, chaotic systems that display regions of constant chaos. Now, the problem is the following. In most of the literature, we can see chaos-based encryptions or methods for cryptography that they are based on a very specific file type. What does this mean? Basically, it means that I make I introduce a cryptography method for images, for voice encryption, for PDF, basically text encryption. So each encryption method is data type file data file oriented. And that becomes an issue for a very specific reason, because from one moment and after, it becomes an issue because you have 20 encryption algorithms for text, 50 encryption algorithms for image, and etc. So this might be useful for industrial purposes. For example, for a pharmaceutical company, it might be good to have a very specific oriented encryption for to encrypt MRIs, for example. However, if a user like me that uses the computer for everyday applications, and he wants to encrypt his data, to have 10 different types of encryption methods to use for 10 different files that I want to encrypt, because I have 10 different data types for each of every 10 different files. This is not a very friendly, user-friendly method or approach. So we thought the following: since we can, every byte can be transformed to an integer value from 0 to 55. This means that a byte stream can just as easily be transformed to the vector of integers between the values of zeros and 255. So our idea is that instead of getting interested in the data of the file, we are interested to take the byte stream of the file, basically the all information that is included in a file. We want to take that information through its byte stream and encrypt that byte stream. So the way we do it, first of all, since it's chaos-based encryption, we introduce a new chaotic map, and you can see it in equation 1. And this is a modulo-based chaotic map, and the function that is inside the modulo is taken from is a Taylor expansion of another function, which of course you can see in our paper, but for the sake of presentation this is omitted. And here on the left you see the bifurcation diagram of the map, and on the right you see the Lyapunov exponent of this map. And what we can see is that has large regions of constant chaos, and also it has large values of Lyapunov exponents. And so, and this is a very first good sign that we have chosen wisely our map for our method. The second thing is that we were also interested this map to have to present at least some uniformity. So we also computed the density bifurcation diagram, which is basically gives us a statistical how is it called? So basically for each R, we can see the distribution, yes. We see that the statistical distribution with respect to the parameter R on the left, and basically when you have a yellow color, you see here, this means that we have a high concentration of values, and we have dark blue where we don't have that much concentration of values. So basically the best should be between 0.2 and 0.3 to imply uniformity. And here we see that this is more or less indeed the case, that for each R, the values are have a color between 0.2 and 0.3. And this is also being verified by taking the histogram when R is equal to 3. And you can also see that indeed it's very close to uniform, this histogram. So again, we are very happy about that. So the next step is to create a pseudo-random bit generator based on our the chaotic map we introduced earlier. So we take 3 sequences, the X, Y, and W sequence. The X and Y sequence are purely sequences based on map 1, and the W sequence is a sequence that is computed based on the values of X, Y, and also W. So you can see here how W values are computed. Then by using the X, W, and Y sequences, we produce integer values within the interval of 0 to 255 by using this rule. And then these values, we convert them to 8-bit sequences. Then this bit sequence, we produced 200 million bits, and we used the NIST tests to check if indeed the bit sequence we produced is pseudo-random. And from the table you see here, it is indeed, this is indeed the case, that we have passed all the tests, and so our pseudo-random bit generator is successful. Then we introduced basically the encryption, and here on the first part you see the encryption, and on the downside you can see the decryption. First, we load the file Bytestream. So basically, we take the Bytestream and we translate it in the interval 0 to 255 for each byte. And then we split this Bytestream to sub Bytestreams that have equal length. And we also take the chaotic map, and from the chaotic map, we take with initial value x1j, we obtain 1 times k matrix that will gives us the permutation order, and then for each sub byte stream, we permute it. Furthermore, we also take our PRPG and then the permuted sub byte stream, we do it XOR with our PRPG to take the encrypted sub byte stream, and this is a repeated process until there are no sub byte streams remain. Then we can send the encrypted byte stream, and the receiver can easily reverse the steps and again take the original byte stream again. So we used this method and we applied it to 5 different types of files, to a PNG, docx, PDF, MP3, and an STL file. Each one of them, you can see that they have their own size for the PNG, for the docx, for the PDF, the MP3, and the STL file. And we use the initial conditions to be defined like that, and of course according to the step 1 that was introduced earlier. So we performed a series of tests to check the robustness of our encryption method, and the first I'm going to show you is the NBCR and the UACI test. B, because we are working with byte streams, not pixels. So instead of NPCR, we have NBCR. And here you can see that we, in the table, you see the critical values. For the NBCR test, the values, the computed values should be larger than the critical values. And the critical values for the UACI have an upper bound and a lower bound. So the UACI numbers should be in between the lower and upper bound. And again, in both NBCR and UACI tests, we pass the tests. So first of all, our encryption through this test is successful. Then we also used entropy, mean absolute error, mean squared error, and PSNR tests. And again, in all these cases, successfully for every file type, the tests are successful. And of course, we also performed a correlation test, and we produced the correlation coefficients between the plain text and the encrypted test. The plain text with respect to its adjacent bytes, and the encrypted adjacent bytes. And again, we also have successfully passed our tests. And of course, the key space and the sensitivity part, of course, we know that for encryption to be robust, to brute force attacks, the key should be higher to 2 to the power of 100. And in our case, because of the key that we're using, the encryption system, the upper bound for the key space is 2 to the power of 800. And because this system is chaos-based, any minor change in the parameters will result in a completely different outcome. So the sensitivity is also ensured. Here also we have performed the histogram analysis, and here on the right for each file type you can see the original histogram, and on the left side you can see the encrypted. And to finally finish this presentation, we have introduced a new one-dimensional chaotic map that has large regions of constant chaos and highly Apunov exponent values. Based on this map, we have introduced a pseudo-random bit generator, which successfully passed all the NIST tests. And we encrypted successfully a variety of file types, and the resulting byte streams were confirmed to be random and secure through a range of different tests and metrics. To further extend our work, we're going to include a chaos-based partition for the byte streams instead of just partitioning the byte streams to equal parts. Instead of having a two-step chaos-based encryption scheme, we want to introduce a third step, a modulation step. Either that might be through S boxes or a typical modulation step in order to increase the complexity of the encryption. We also want to apply parallel computing because this will allow us to have even faster encryption times, and especially in larger files, where then in large files it becomes apparent whether the encryption is good or not, in the sense that if it takes 1 hour to encrypt the file, then this is not might be very useful. And finally, we want to design a graphical user interface which will allow an easy access to any user. Thank you very much.
Thank you very much, Mr. Karalabidis. It was very nice, your lecture. Have we any questions, please?
I have a question.
Yes, Professor Markovsky, please.
Dear Nikos, I am familiar with your work. However, from the practical point of view, if the reproduction model can present your sequences with an error about 5 or 6% or less, in practice, these sequences can be broken. And my question is, have you tried using artificial intelligence to build and such approximated reproduction model for your sequences?
Could you please rephrase the question?
Okay. Look here. From the practice, your analysis that the attacker reproduction your sequences absolutely.
Mm-hmm.
But on practice, from the practical point of view, if we can build the approximate reproduction model with error less than 6 or 5%, in real, these sequences can be broke. So your message can be broke. And my question is, have you tried using artificial intelligence to build such approximate reproduction model?
That is a very interesting question. Indeed, we haven't used AI for cryptanalysis, and this is a very nice question indeed to be explored, because if an AI can brute force the encryption scheme, then basically anyone can have access to the encrypted information, and it should be something to be explored.
Thank you, but I need that we work this. This we continue your work. Yes, on this
Yes.
direction.
Yes,
In
yes.
this direction, because of it's very important for practice, from the practical point of view. Yes.
Yes. Thank you, Professor.
Thank you, thank you. Professor Lazaros Moisis wants something to say. Please, Professor Moisis, you write a comment, so we're listening also.
Hi, Professor. Thanks a lot. I'm also a co-author of this work, and from my
Yes.
studies, I see there are many deep learning techniques for cryptanalysis. So here, as regarding to your question, Professor, it also has to do with what we're trying to attack. Are you trying to attack the map? So you can replicate the map. Are you trying to attack the plain text? Are you trying to attack the communication channel? So what I also say in many papers, and especially when I do peer review, you need to have each step of the process being secured. Now, if someone tries to replicate, as you said, the map using deep learning or something else, simple chaotic maps like the logistic map are super easy to decrypt. I mean, the code for replicating or estimating the logistic map is just like 10 lines of code. Highly nonlinear maps that utilize modulo or other nonlinear functions will be harder. Not impossible, but we're trying to go towards that direction where we are using highly nonlinear maps, a bit more time consuming, but they will be very difficult to estimate their key parameters. And possibly we can do that. So classic maps are out of the question, like Lorenz system, logistic map, these basic maps, they're not usable. So we need to go towards the direction of building secure maps.
Thank you, Professor Moisis. Thank you very much. Thank you. It was very nice, your presentation. Congratulations. Thank you very much. Thank you, Mr. Haralambidis and Moisidis, and of course for questions. Next paper will be presented